DSPCP, a data scalable approach for identifying relationships in parallel coordinates. A number of challenges exist when using standard parallel coordinate plots. Take the first two dimensions, for example. The overlapping lines of these two dimensions makes interpretation difficult. This overdraw creates a number of problems. In particular, it can disguise the true relationships between dimensions by hiding mixed trends and noise within relationships, and it makes it difficult to differentiate outliers from the primary trend. We introduced the DSPCP as a scalable mechanism to address these limitations in the standard PCP. For example, here the DSPCP disambiguates three approximately linear trends within the data by representing them as three different surfaces. In addition, it displays the non-uniform distribution of points and their associated noise. We now describe some specifics of the DSPCP visual encoding using 6 sample datasets. On the top are 3 positive relationships, one perfectly positive, one noisy, and one nonlinear. On the bottom are 3 negative relationships, one perfectly negative, one noisy, and one nonlinear. The DSPCP uses 3 main visual encodings. The first is the overall shape and color of the region. We differentiate the positive trends by their rectangular shape and red color from the negative trends with their bow tie shape and blue color. In the positive relationship case, all shapes are identically rectangular. In the negative case, the linear relationships are bow ties, but the nonlinear bow tie is rounded and skewed, indicating the nonlinearity. The next visual encoding is a consistency map. The consistency map is found within the shape and serves as an indication of the noise level within the data. In the perfectly linear cases, the consistency maps are well organized. In the noisy cases, the shape of the map begins to spread out as an indication of that noise. In the nonlinear cases, the map helps to show the nonlinear shape of the data. The final visual encoding is a data distribution. This distribution is a pink histogram along each of the axes. This can serve as an indication of the uniformity of data points. Lower regions are indications of outliers or weaker trends. In the case of these data sets, the data are mostly uniformly distributed, with the exception of some small variation in the nonlinear cases. To support identifying multiple trends within the data, we use a clustering and layering approach. We support both a global clustering across all attributes and a local clustering between 2 attributes. Once clusters of points have been identified, separate shapes and consistency maps are formed for each and layered. Interaction enables flipping between layers. We also use interaction to support other common PCP operations, such as selection and brushing. When an area is brushed, a new cluster is formed, and a new shape and consistency map are calculated. We demonstrate our approach using the Higgs dataset containing 28 attributes and 11 million data items. This data was produced using Monte Carlo simulations that capture the kinematic properties measured by the detectors in a particle accelerator. We show 7 attributes using the standard PCP, angular histogram, opacity PCP, and the DSPCP. It's clear from both the scatter plot and the PCP that the Higgs dataset is both large and noisy. Beginning with the lepton, phi, and energy mag attributes, using the standard PCP, a negative relationship appears, but the level of the noise is difficult to ascertain. Looking at the angular histogram, a uniform distribution of points is apparent, but not much else. The opacity PCP makes the noise level fairly clear. Using the DSPCP, a weak relationship is seen in the very loose bow tie. Furthermore, the noise in the relationship can be seen in the freckles of the consistency map. Next, we consider the relationship between jet1 eta and jet1 phi. Because of the overdraw and complexity of the relationship, it is difficult to interpret the relationship in the PCP. If anything, it appears slightly positive, but no conclusions can be made. By itself, the angular histogram does little to improve our understanding of the relationship. It mostly reinforces the previous conclusion. Adding the opacity PCP helps to clarify the noisy nature of the relationship, but it does little to disambiguate the relationship direction. In fact, the Pearson correlation coefficient of jet1 eta and jet1 phi is negative 0.1, indicating a weakly negative relationship. Our approach, on the other hand, identifies this relationship for what it is. The main trend in the data is a large negative relationship. Large size of the bow tie and freckled pattern contained within indicate the relationship is noisy and weak. For technical details and additional data sets and examples, please see our paper. Thank you for watching.